the real and imaginary parts of the self-energy. Okay, it's not a very complicated calculation, but now let's see what this tells you about the dispersion. Here's the dispersion of copper, and here you can see, if you zoom in, close to the Fermi energy due to electron-phonon coupling, you get this kink right here at the Fermi energy. And it's this kink that we would like to measure with STM. And here's our data. Here's the kink. Actually, let me show you. Here it is. Here's the data. And you can see close to the Fermi energy, there's a tiny kink in E versus K. Now, what do we want to do? Well, what we want to do is we want to actually figure out what this real part of the self-energy is. Once we have that information, we can invert it to get alpha squared F. That's the idea. So how do we do that? We take something that should look like the bare dispersion, subtract these two from each other, and here it is. Here's the self-energy due to electron-phonon coupling in copper. And now we want to compare this with something, and remember the random alpha squared F I was talking about. As it turns out, it's actually a calculation for copper. So now we can compare the data, our data, with the alpha squared F that we got from the calculation. And you can see these are very close to one another, okay? Just to give you another reference point, here's another such experiment done on silver 111, and you can see that the data is all over the place. So compared to that, at least we've done a reasonable job of measuring this electron-phonon coupling. But the problem is the following. If you look at the comparison between our experiment and the calculation, you see that the experiment is missing all of these wiggles. Look at this, all these wiggles. And the question is, are these wiggles important? And it turns out these wiggles are critical. These wiggles come from these peaks in the alpha squared F. Each of these peaks represents a phonon, okay? So if you don't capture the wiggles in your experiment, you will not be able to invert it to get this alpha squared F, all right? So basically, you need much higher precision. Okay, so the devil is in the details, and quasi-particle interference would be great if we could do it with much better resolution. But then there is actually another technique which we can use called Nanolevel Spectroscopy, and I'll show you how using that technique we can actually get electron-phonon coupling to great precision. Okay, before I go ahead, how much time do I have? Who, Pierce? I've been going 15 minutes. Okay, all right. Approximately. Okay. Okay. Yeah, I'm sorry about how technical this talk is, but I'll just keep going. So in scanning tunneling microscopy, the other thing we can do is we can turn on a magnetic field, and we can look at lambda levels. And as it turns out, the lambda level spectrum can be used to get dispersion. And what I want to show you is that if you use the lambda levels and get the dispersion from that, you can actually get the self-energy effects that I was talking about to very, very great precision. And you can calculate alpha squared F. And you can calculate the electron-phonon coupling lambda. And so this is a very powerful tool. I was hoping to get to the second part of my talk, which talks about strain effects, but I don't think I'm going to be able to do it. Maybe you can ask me questions.
You can introduce
yes. Okay. So to talk about Lambda level spectroscopy, I want to give you a bit of background on the material that I'm going to look at. It's not a very simple material like copper. In fact, it happens to be a topological crystalline insulator. Topological materials are where you have these very beautiful surface states which have linear dispersion. Normal electrons, like I showed you earlier, the relationship between energy and momentum is quadratic. But in these special materials, you have Dirac dispersions. Dispersion and electrons are expected to behave like massless Dirac fermions. So one example of this material is this TCI, which was predicted by Liang Fu in 2011. And this is the material we're going to study. And in particular, the material I'm going to look at is lead-tin selenide. And it has a whole range of very beautiful properties. It has temperature dependence. You can actually turn it into a superconductor. It has interesting thermoelectric effects. And it has very high mobility, meaning you can actually make the samples pretty clean from an electronic perspective. So this is the crystal structure of this material. What we usually do is we break it in vacuum to reveal a flat, clean surface. And if you do that, then this is the surface it reveals. You should see a square arrangement of atoms. And in fact, that's what we see here is STM topography. And each dot is a single atom, and you can see they are arranged in a square lattice. So you can take the DI/dV spectrum that we normally like to take. It represents the density of states, and here's the Fermi energy. And this V shape tells you that the dispersion for these two-dimensional electrons is actually linear. Now we can turn on a magnetic field. And in a magnetic field, electrons fall into these cyclotron orbits. And quantum mechanically, these cyclotron orbits are quantized. So in a magnetic field, you should expect, instead of having a continuous spectrum of possible electronic states, you should have discrete energies which are occupied by electrons, and other energies cannot be occupied by electrons in a magnetic field. And just like a particle in a box, each of these levels is labeled by a quantum number. So, the interesting thing about these Lambda levels is that the area that the Lambda levels occupy in momentum space, right? This is the area, and this area is just pi k squared, and this area depends on the magnetic field as well as this quantum number n. This means that if you could actually figure out the energy of these Lambda levels, you automatically won't know what the momentum of the electrons is. There's a direct relationship between the two. Okay? So by turning on a magnetic field and looking at these Lambda levels, we know energy and we know momentum, so we can actually plot the dispersion. So here's an example. Let me just go to the example. This is lead-tin selenide, and you turn on a field, look at all these peaks. Each peak is a Lambda level. And now, if you were to plot energy versus momentum, this is actually momentum, you get beautiful linear dispersion. And then the other interesting thing in this system is you get a break at a certain energy, and this break is due to something called a Lipschitz transition, where the electronic structure turns from two electron pockets to an electron in a whole pocket. That's a technical detail. But in any case, you can see, using this Lambda level technique and plotting all the energies of the peaks, you can actually get dispersion. Now let's see what this technique does for us in terms of understanding electron-phonon coupling. So here's lead-tin selenide again. Turn on the field, get the Lambda levels, plot the Lambda levels as a function of magnetic field, and now notice each of these dots is a data point. And if you look very carefully, here's the Fermi energy. There's a tiny wiggle about the Fermi energy. Okay? And now we want to use this wiggle to get information on electron-phonon coupling. And the key thing here is, like I told you earlier, if you were to subtract the bare dispersion from the data that we got, you get the self-energy, the real part of the self-energy. How do you invert the self-energy to get alpha squared f? That's not a trivial task. So to do that, we used an algorithm called maximum entropy method. And this is an iterative process. And we stop when the whole thing converges. Okay? That's how we get alpha squared f. Okay. So here it is. Here's the real part of the self-energy, which we got by taking our data and subtracting a background. And here's the inverted alpha squared f that we get from the data. The reason we went ahead with this at all is because if you look carefully, this self-energy, unlike the copper self-energy, has a bunch of little tiny wiggles in it. And if you notice the y-axis, this is millivolts we're talking about. So the only way you can do this is if you have millivolt or sub-millivolt resolution. Okay, and then the question is, how well did we do? Well, actually, so here each peak is a phonon peak. So you can actually compare, there's no actual measurements of this in this material, but you can compare the phonon energies with theoretical predicted bulk phonons, not surface phonons, and you can see that we're within a millivolt for most of the phonons in this system, okay? So in that sense, we've done pretty well. Okay, and we can get lambda, and this is very small. So this is all I have to say about electron-phonon coupling. And if I have 5 or 10 more minutes,
well, yeah, maybe 5 minutes.
5 minutes, okay. I'm going to switch tracks and go on to the next part of my talk, which is strain effects. Okay, so just to remind you, I'm talking about getting quantitative information from the scanning tunneling microscope. In this case, what I'd like to show you, if I have enough time, is how we can get quantitative measurements of strain and also quantitatively determine how strain affects the local electronic structure. So to do this, strain is a very powerful knob in condensed matter physics. There's some beautiful experiments showing how you can use strain to actually enhance TC by a factor of 1.5 in strontium gluconate. You can get pseudo Lambda levels in graphene and so on. So strain is really a very powerful knob, underutilized in fact. So in our case, what do we expect strain to do? In our system, we have these Dirac cones, and what we expect, theoretically at least, is that strain should shift the position of the Dirac cones in momentum space. Okay? So this is what we set out to look for. In extreme circumstances, non-uniform strain should also create, in our case, pseudo-Lambda levels, meaning strain should in fact act just like a magnetic field, and it should give you Lambda levels in our system. So that's what we were looking for. Okay. So how do you generate strain, especially spatially varying strain? You can do it using epitaxial thin film growth. So here, actually, this is a work that was done quite a while ago in 2002. They grew lead telluride on lead selenide, I think. And when they do that, they see this superstructure, okay? And the superstructure is actually, each little dot here is about 200 angstroms. It's pretty big. And these dots are represented like a buckling, a two-dimensional buckling, and they encode strain. Okay, so this is what we wanted to do for our topological insulator. And so what we did is we cleaved lead selenide and we deposited tin telluride on top of it. Okay? And so what happens initially, you cleave the material, you start depositing, the first layer conforms. Okay? The first layer of tin telluride would conform to this atomic lattice. But very soon the strain builds up and you start getting all these dislocations forming in order to relieve the strain. So as you deposit more and more layers, you get many more dislocations building up in the system. And so that's what you see. I'll show you images of what happens as you grow these thin films. Let me actually, okay. So here's less than a monolayer, and you can see that it's very well conformed. So this is a highly strained, uniformly strained tin telluride layer. And then 2 to 3 monolayers, you begin to see these lines. Each of these lines is a dislocation. And as you increase the number of monolayers, you get more and more lines until it saturates. And at 40 monolayers, you get this network of dislocations. And at 40 monolayers, all the DC strain is gone from the system, but you're left with this two-dimensional buckled thing that encodes AC strain. Okay, So now we can actually take high-resolution images and measure the strain in this material. Notice that even though the size of this image is so large, if you zoom in, you can actually see the individual atoms. And because you can see the individual atoms, you know the entire strain field in this system. So let me just show you. We use some kind of algorithm, so we don't actually go in and look at each atom and ask the question, how far has it moved from its equilibrium position? We use an algorithm to actually determine the strain, and here is a strain map, okay? So this strain map just tells you regions of compressive and tensile strain, but we can actually do much better than this. We can actually calculate the strain tensor as a function of position, right? What is the strain tensor? If you know the displacement field U, right, then the strain tensor is simply derivatives of the displacement field in different directions. So we can actually calculate the microscopic strain tensor, and here it is. This is the strain tensor. These are its diagonal components. And now we can see that this is a map of the compressive and tensile strain like I showed you earlier. But interestingly, in the same material, we also have uniaxial strain, okay? So compressive and tensile strain is when all the four atoms are moving in together and out together. Uniaxial strain is when two atoms move in, two atoms move out, or vice versa. So you can ask, how can you have these two kinds of different displacements realized in the same sample? And the way you do it is, these things live in different parts of the sample. So if you look carefully at the strain distribution, so here's isotropic compression, here's isotropic stretching, here's uniaxial strain in one direction, and here's uniaxial strain in the perpendicular direction. So in one sample, we have everything. Now what we can do with scanning timing microscopy is we can go in, look at all these different regions and ask the question, how do these strains affect the electronic structure? And I think I have to stop, right, Piers? Okay, thank you for your attention.
Thank you for a lovely talk. We have lots of time for discussion. Any questions? Yes, Jim.
In the dispersion, the kinks, how, in the dispersion that you measure that has kinks in it, how do the phonon bumps that eventually appear in sigma prime show up in the dispersion with the kinks?
Yeah. So they show up as kinks, as little wiggles in the sigma prime. That's why you need high resolution, because those little wiggles are really, really, really tiny. But like I showed you in copper, there were no little wiggles, so we couldn't have seen the phonons. But because in the Lidar Level Spectroscopy, you're looking at peak positions, so we have a huge amount, much better energy resolution. So we can actually track the peak position really, really well, and we see little wiggles in the real part of the self-energy.
Have any of those little wiggles ever been seen in any of the ARPES experiments?
I seriously doubt. They have, everything's going to be broadened by the ARPES resolution. I'm talking about energy scales of less than 1 millivolt. And so we can see from copper, you can fool yourself into thinking it exists, but actually you really need high resolution, otherwise you can fool yourself.
So it would be a pretty experiment to take one of the materials where the kinks have been seen and are thought to be due to phonons with ARPES, and then do exactly your experiment, and then I could picture a nice curve with sort of ARPES and then your stuff laid on top with little wiggles. Is that in principle possible?
Absolutely. You should do quasi-particle interference for that, and that's absolutely possible. In fact, we're trying to do that for strontium gluconate.
No. Ladies first.
Thank you so much, Chris. Thank you for your very interesting talk. I have two very small questions and maybe comments. One is I would like to know at what temperature you've done these measurements with STM, because the temperature has to be quite low to be able to see these wiggles, I suppose. And the other question is how you cannot completely rule out the interaction with other bosonic degrees of freedom.
Absolutely.
But what is really important is that you have compared with the results with the prediction of the phononic mode. So that is also already an answer to that. But I suppose these wiggles can also show up when you have interaction with magnons.
Yeah. Yeah, I completely agree with you. And in fact, that's the interesting, exciting thing that we'd like to do. The question is, what is the electron-boson coupling strength? If you have strong enough coupling, we can see it. But if the coupling is slightly weak, then you can already see that. Actually, I shouldn't say that. So we were at 4 Kelvin, not even at millikelvin temperatures, so not very cold. And in the lead, in the TCI case, the lambda was 0.1, tiny, really tiny. So we could actually resolve that. So I take that back. I think we should be able to see electron spin acceleration coupling as well.
And what temperature was it?
Ours was 4 Kelvin, but it would be nice to do this at lower temperatures, yes.
So what is your resolution in the momentum direction? And what are the limiting factors for the resolution in energy and momentum?
Yeah, that's a really good question. Momentum, it depends on which, we have 2 techniques, quasi-particle interference and Lambda level spectroscopy. In the Lambda level spectroscopy, we have momentum, we've averaged over K-space, right? There we have pretty high energy and momentum resolution. It's only limited by the modulation that we put on our bias. That's how we do the spectroscopy, and the temperature. So it's less than 1 millivolt. We can even do microvolt resolution for the Lambda levels. In the quasi-particle interference case, the quasi-particle peaks are they're fuzzier. So there you can ask all kinds of questions. Their momentum resolution is limited by the size of these DIDV maps that you take. So that's much, but there you have direction information. So you can actually ask the question, how does the electron-phonon coupling change as you change direction? So there you have more information.
Okay, thanks.
Thanks. I have an ancient memory that may be false, but I remember that copper is famous for having a prominent surface state.
Yeah. That's what that was.
Oh, so you're actually looking at the surface state.
Yeah.
So then why would you expect the surface state to have the same electron-phonon coupling as calculated in the bulk?
Absolutely you wouldn't. That's why all I can tell you is that the peaks are close within a millivolt, but certainly on the surface they might shift by about a millivolt. But the fact is, STM is known as a surface tool. It's beautiful to look at surface states, but recently we've been discovering we can look at bulk states quite as easily with STM, as long as the electronic structure is quasi-2-dimensional. So that's the requirement, really.
Sorry, Jim.
So a very basic question. You showed the QPI for copper.
Yeah.
Why is that not a full disk, and why is it not isotropic?
I don't know the answers. We were looking at copper. We clean our tips on copper. So we weren't really setting out to study copper. And so I get this question a lot, and I have to go back and see, is this something systematic? Can we repeat it? Was it something to do with the tip, or I don't know. Sorry, I'm sorry, I don't know. Yeah.
Jim had a follow-up question.
I can think of maybe one other twist on the possible comparison to ARPES. I have the impression that, at least in some cases, when ARPES sees a kink, the actual origin of the kink is sometimes in dispute. Is it phonons? Is it a plasma? Is it a this? Is it purely electronic? And so on. So I could imagine that you might have a look at one of these disputed situations, and from the detailed bumps and wiggles, you might be able to say very clearly without an indirect inference what's the origin, and in some cases it's a high-stakes game, so yeah.
Yeah, I think so. I think there's a lot of stuff to be done there. Yeah.
I just have to add one self-serving statement here, which is if you do the point contact spectroscopy, you are measuring the bosonic excitations and the L-Ashford function, but in the bulk. So you don't have to, you are bypassing the surface states. So I think it'd be very interesting to compare your data and what we could possibly do on copper, and just to see how we can separate the bulk from the surface states.
But you get a spectrum.
Yeah.
So then I would have to ask, how does this affect our DIDV spectrum? And so that's a more subtle thing for us, because lambda is very tiny. It's like 0.1 or 0.3 in copper, between 0.1 and 0.3. And so the effect of it on the actual DIDV spectrum is tiny. And for us, it's very difficult to distinguish that from other bumps and wiggles that we see. It's a metal, so we see little tiny bumps and wiggles, so we can't tell the difference. We can only pick up bosonic modes in the spectra when it's a superconductor.
Oh, see, that's the advantage of point contact, is it doesn't need to be superconducting.
Right.
It's just scattered off of a quasi-particle, so you can differentiate that.
So then that would be really cool. Yeah.
Harrison's theorem doesn't hold.
One last question.
Okay, so you quickly glossed by Lipschitz transition. Since I have some interest, I wanted to know how interesting is it for you or in general to think of in terms of Lipschitz transition in these materials?
So Lipschitz transition is really interesting because it gives us a peak in the density of states. And we can see the peak in the density of states. That means if I could position my Fermi energy at the peak, I might get an instability, and I might get different kinds of CDWs or some other instability, even superconductivity. So in that sense, the Lipschitz transition is very interesting.
But have you actually found a correlation between seeing a Lipschitz transition and some of the effects you just...
The Lipschitz transition is too far from the Fermi energy. In fact, in this sample, the Fermi energy is inside the band, so the Lipschitz transition is below that. And everything I was talking about is within 30 millivolts of the Fermi energy.
Okay, so it's lunch, and the lunch goes on till 1:30. We will resume at 1:30. So